Okay, so what about capacitors that are in parallel with each other? Okay, like this, when they're arranged like that. How do you handle that? All right, so if you do that, what you need to recognize is that the voltage across the battery, if that's, say, 2 volts, when you go up, if your path integral goes like this, all the way around, back to that point, then the only place that you've lost voltage is across here. You gain some voltage, you got to lose it. And so this will be the same voltage as that. So this is the same voltage as the battery. This is the voltage across the battery. How about the voltage across here? Well, if I start here and I go up 2 volts and I go around like this, I'm not losing any voltage because this is metal that has no field in it. And then I come down here, I have to have lost all that voltage right here. So this is also the voltage of the battery, and this is also the voltage of the battery. Another way to look at that is if I start here and I go around this loop, I have to lose it all. So see how the field lines go this way? And these field lines go this way? Oh, I guess we haven't gotten you there yet. Why do those field lines go that way? Because this is a positive terminal and this is negative. And so if you're an electron, you come on over here and you plop onto there, which means that you left this spot, which means this spot is positive. And if you're an electron, you come over here. So this spot's negative. So if I start here, if I go this way, am I not going against the field? See how I'm going up against the field? So I'm going to gain 2 volts, and then I'm going to drop 2 volts. So same voltage there. Okay. Now if I wanted to take this and replace it with just one capacitor, that would store as much charge as all 3 of these. Well, that would have to be a pretty big capacitor. So I want to replace it with one equivalent capacitance that will store as much charge. See, all this charge, once you store it, it's available to be used. And so that charge has to be equivalent to this when you add them up. So C equivalent, the Q equivalent, or the Q total on this one has to equal. That has to equal Q1 plus Q2. That's a Q. Q2 plus Q3. And so I'm going to replace the Q's with, going back to this equation, C equals Q over V. Well, apparently that's Q is equal to CV. So I'm going to say that for this one, the charge on this will equal the equivalent capacitance times the voltage. Now the voltage is still VB, because when you go up so much, you got to come down so much. That will equal C1 times V1 plus C2 times V2 plus C3 times V3. Okay, well, the V's are all the same, though, because of the loop rule. When you go around, you got to drop all the volts. And so V1, V2, and V3, they're equal. And so they're going to cancel out. And what I have is C equivalent is equal to C1 plus C2 plus C3. So that's how you get the equivalent capacitance. You just add them up. It's the reverse of resistors. Okay, let's do a quick problem and call it a day, or call it a video. All right, so here we go. Let's make this battery can be 4 volts. And let's make this first capacitor, we'll make it, let's go with 6 microfarads. And this one right here is going to be 2 microfarads, or 3 microfarads. Okay, so let's figure out then just what the charge will be on these. Okay, and so the way you can do that, Actually, you don't even have to make, let's find the equivalent capacitance first. The equivalent capacitance is just C1 plus C2. So that would be 9 microfarads. So we get a much bigger capacitance. It's almost like, can you imagine if you took these and just squished them together so that they would be just one big plate? If you brought them close together, they're at the same potential anyways, so no charge will go across. This is the same potential as that. And so when you push them together, it's just like one big plate. And so because C equals epsilon naught A over D, we've essentially made the area much bigger, and that's why C is much bigger. Okay, so to get the charge on each plate, I just know there's 4 volts across here and 4 volts across there, so I can just multiply this by this so to get the charge. So that's going to be 24 microcoulombs. So for that one, it's 24 microcoulombs. And for this, it's 12 microcoulombs. We probably could have reasoned that second one a different way. Rather than multiply these two together, we could have reasoned that this has only half of the capacitance of that. So it should only get half the charge. Since they're both at the same voltage, this having half the capacitance will only be able to store half the charge. So 12 microcoulombs compared to 24 microcoulombs. All right, so that's how you handle capacitors that are in parallel. You just add up, to get the equivalent capacitance, you just add up C1 plus C2 plus C3 plus however many more you got. All right, thanks a lot. Bye.